Welcome to this scientific lecture on fractional and anyonic quasiparticles in two-dimensional nanostructures, a frontier of quantum condensed matter physics. In two-dimensional electron gases and nanostructured materials, we observe emergent quasiparticles with exotic properties that defy conventional quantum mechanics. Let us first review what we expect from ordinary quantum particles before exploring the exotic behavior. In conventional three-dimensional materials, all fundamental and composite particles obey strict quantization rules that have been verified for over a century. Electric charge is always an integer multiple of the elementary charge E, equal to 1.6 times 10 to the minus 19 coulombs. Spin, angular momentum, comes in half-integer multiples of h bar, the reduced Planck constant. Particles must be either fermions with half-integer spin obeying Pauli exclusion, or bosons with integer spin that can occupy the same state. When you exchange two identical fermions, the wave function picks up a minus sign. For bosons, it stays the same. These are the only two options in three dimensions. But why should the dimensionality of space change these fundamental rules? The answer lies in topology. Quantum exchange statistics are determined by the topology of allowed paths when particles move around each other. In three dimensions, if you move one particle around another, the path can be continuously deformed and shrunk. This topological constraint forces only two exchange statistics. But in two dimensions, particles are confined to a plane. A path wrapping around another particle cannot shrink to zero without crossing the particle, which is forbidden. Mathematically, the first homotopy group of the punctured plane is the integers, not just the two-element group. This opens the door to anyonic statistics. The experimental discovery of fractional quantum Hall physics revealed nature exploiting this two-dimensional freedom. Take a two-dimensional electron gas, cool it to millikelvin temperatures, and apply a perpendicular magnetic field of several Tesla. The strong magnetic field quantizes electron motion into Landau levels, discrete energy levels analogous to harmonic oscillator states. The Landau level energies are h bar omega c times n plus 1/2, where omega c is the cyclotron frequency EB over effective mass. When you tune the magnetic field so that the filling factor nu, the ratio of electrons to flux quanta, equals 1/3, a new quantum state emerges. The filling factor is the electron density times area per flux quantum. At 1/3 filling, electrons form a strongly correlated incompressible quantum liquid. The Hall resistance becomes precisely quantized at 3 times h over e squared, with stunning precision better than 1 part in 10 billion. For the Laughlin 1/3 state, the exchange phase is precisely pi over 3 or 60 degrees. Moving one anyon around another accumulates a phase of e to the I pi over 3. This is neither fermionic -1 nor bosonic +1, but something in between. Generally, for the 1 over m Laughlin state, quasiparticles carry charge plus or minus e over m. This is fractional charge, forbidden in ordinary matter. Experimentally, this fractional charge was confirmed through shot noise measurements in quantum point contacts by de Picciotto and Resnikov groups in 1997. Shot noise power is 2 times effective charge times current. The measurements definitively showed E star equals E over 3, confirming fractional charge. But fractional charge is only half the story. These quasiparticles also obey anyonic statistics. When you adiabatically exchange two identical anyons, the wave function acquires a phase that is not restricted to plus or minus 1. The wave function transforms as psi of R1 R2 goes to e to the I theta times psi of R2 R1, where theta can be any angle. For the Laughlin 1 over m state, the exchange phase is precisely pi over m. For the 1/3 state, theta equals pi over 3 or 60 degrees. Moving one anyon around another accumulates a phase of e to the I pi over 3. This is neither fermionic -1 nor bosonic +1, but something in between. This anyonic phase arises as a Berry phase, a geometric phase accumulated when the system traces a path in configuration space. The Berry phase is the line integral of the inner product psi gradient r psi dot dr, integrated over the closed exchange path. Think of it like the Aharonov-Bohm effect. Moving a charge around a flux tube gives a geometric phase. even without classical forces. In Aharonov bohm, the phase is E times magnetic flux over h bar, or 2 pi times flux over flux quantum. Anyons see an effective flux attached to each particle. A powerful theoretical framework views anyons as electrons with attached flux tubes, forming composite fermions. Jindra Jain proposed that we can understand fractional quantum Hall states by transforming electrons into composite fermions. This explains the prominent sequence of filling factors, nu equals p over 2p plus or minus 1, like 1/3, 2/5, 3/7, and so on. Picture each electron carrying 2 flux quanta. In the transformed frame, these composite fermions see a reduced effective magnetic field. The effective field is B star equals B minus 2 times electron density times flux quantum. At nu equals 1/3, B star creates a filled composite fermion Landau level. This flux attachment mechanism is precisely what gives rise to anyonic statistics. The attached flux creates the statistical phase. The exchange angle theta equals 2 pi times the flux per particle divided by the flux quantum. This directly connects flux attachment to statistics. Even more exotic are non-abelian anyons, where exchange does not just add a phase, but performs a unitary transformation in a degenerate subspace. At filling factor 5/2, the Moiré state supports quasiparticles that are non-abelian anyons. The Moiré wavefunction is a Pfaffian times a composite fermion state, supporting Majorana zero modes at quasiparticle locations. With 4 non-abelian anyons, the system has a degenerate ground state manifold. Exchanging anyons rotates between these states. Exchange is described by a unitary matrix Uij from the braid group, not just a phase. Sequential exchanges do not commute. This non-commutativity is the foundation for topological quantum computation, where braiding anyons performs quantum gates. Recently, moiré materials and twisted structures have opened new arenas for observing anyonic physics. When 2 graphene sheets are twisted to a magic angle of 1.1 degrees, flat electronic bands emerge with strong correlation effects. The slight misalignment creates a moiré superlattice with a much larger period than the original graphene lattice. The moiré wavelength is lattice constant over 2 sine theta over 2, about 13 nanometers at the magic angle. In 2023, multiple groups observed fractional quantum anomalous Hall states in moiré graphene, realizing fractional Chern insulators without external magnetic field. These states have topological Chern number 1, given by the integral of Berry curvature over the Brillouin zone divided by 2 pi. Theory predicts anyonic quasiparticles in these states, but direct measurement remains an experimental frontier. The rigorous framework for understanding these phenomena is topological quantum field theory and topological order. Unlike conventional phases with symmetry breaking, topologically ordered states have no local order parameter distinguishing them from trivial states. The topological entanglement entropy is gamma times log of the total quantum dimension d, a universal constant characterizing the topological order. On a torus, topologically ordered states have ground state degeneracy equal to the number of anyon types. The ground state degeneracy on the torus equals the cardinality of the anyon set, providing a topological invariant. The Laughlin 1/3 state on a torus has threefold ground state degeneracy, corresponding to 3 anyon types: vacuum, quasiparticle, and quasihole. Anyons have quantum dimensions and obey fusion rules that generalize the concept of particle statistics. When 2 anyons A and B fuse, the result is a superposition of anyon type C with integer fusion multiplicities NABC. The simplest non-abelian anyon model is the Fibonacci anyon, with just 2 types, vacuum 1 and tau. The fusion rule is tau times tau equals 1 plus tau. This simple rule leads to extraordinarily rich braiding properties. The quantum dimension of tau is the golden ratio phi, approximately 1.618. This is not an integer, reflecting the non-classical nature. The total quantum dimension d is related to the topological entanglement entropy we mentioned earlier. d equals the square root of the sum of squares of all anyon quantum dimensions. For Fibonacci, d equals phi times square root of 2. Now, let us turn to the practical implications for quantum devices and sensors. Qubits encoded in non-abelian Anyonic braiding are topologically protected against local perturbations. The error timescale grows exponentially with system size L divided by correlation length x, providing robust quantum memory. Each pair of non-abelian anyons can encode quantum information in the fusion channel, protected by topology. Fractional charge detection opens new sensing modalities. Measuring E/3 charge units provides higher sensitivity than integer charge detection. The minimum detectable charge scales as E/3 root n, where n is the number of tunneling events, improving resolution by a factor of 3. How do we experimentally verify the presence of anyons in a sample? Current shot noise spectroscopy measures the effective charge of carriers via their Poissonian fluctuations. Zero-frequency shot noise equals 2 E star times absolute current times 1 minus transmission, where E star is the effective charge. Anyonic braiding phase can be measured using Fabry-Perot interferometry in quantum Hall edges. Edge states encircle a region containing anyons. The interference pattern reveals the anyonic phase theta accumulated during braiding. Current oscillates as cosine of 2 pi flux over flux quantum plus statistical angle theta. The theta term shifts the interference pattern. Scanning tunneling microscopy can directly image quasiparticle wavefunctions and measure their energies. Let us put some concrete numbers to these abstract concepts. Consider a GAA's algaase quantum well with density 3 times 10 to the 11 per square centimeter. At this density, reaching nu equals 1/3 requires magnetic field of about 10 Tesla. Using B equals H/E times density over filling factor, we get approximately 10 Tesla. The magnetic length is square root of H bar over EB, approximately 8 nanometers. This sets the typical quasiparticle size. The energy gap is about 0.3 times E squared over epsilon magnetic length, roughly 5 Kelvin or 0.4 millielectron volts. To observe clean fractional quantum Hall physics, temperature must be well below the gap. Boltzmann constant times temperature, much less than gap, requires temperatures below 1 Kelvin, explaining why dilution refrigerators are needed. In twisted bilayer graphene, the relevant energy scales are quite different. Moiré bandwidths are about 10 millielectron volts, requiring temperatures below 5 Kelvin, more accessible than quantum Hall systems. Remarkably, these condensed matter systems connect to fundamental physics in quantum gravity. The same topological quantum field theories that describe anyons also appear in string theory and quantum gravity. The partition function Z on a manifold sigma is the sum over topological states of e to the I times action, independent of metric. Chern-Simons theory in 2+1 dimensions is the paradigm connecting condensed matter anyons to topological quantum computing. The Chern-Simons action is k/4 pi times the integral of a wedge dA, where k is the level determining anyon types. Some researchers explore whether fractional quantum Hall states realize holographic dualities connecting bulk geometry to boundary physics. Despite tremendous progress, many fundamental questions remain open. While theory strongly suggests nu equals 5/2 is non-abelian, definitive experimental proof via interferometry remains challenging. The dream is finding materials with topological gaps exceeding 300 Kelvin, enabling practical quantum devices without cryogenics. Understanding anyon dynamics beyond equilibrium will be crucial for designing and controlling topological quantum systems. Thank you for watching this video on fractional and anyonic quasiparticles in 2D nanostructures.